What up, people? I'm back. Now we're going to be doing some trigonometric integrals. Okay, so not using trig substitutions, but evaluating integrals that have trig inside of them. So sines, cosines, products of sines and cosines, and then secs and tens and all of that stuff. All of that fun stuff. I really hate the way that this is often taught. They often teach this in a very methodical. If the power of cosine is even, do this. If the power of sine is odd, do this. I never learned it that way because, even though it was taught like that to me, I found it kind of hard to remember all of those different, it was almost like a flow chart you had to remember. If m and n, the powers of cosine and sine, are even, do this. If it's odd, do that. I found that the best way to do it is to just sort of recognize why those different properties or those different rules work. And that way, when the question came, it just made sense. Yeah, obviously I'm going to do this because that's how you do questions like this. You can get it into a chain rule function, or you can get it into reverse chain rule, or you can get it into this or that. Anyway, you'll see what I mean as we go along. Particularly, we're going to be dealing with examples where you might have, for example, powers of x or powers of cos x. Say something like cos cubed, okay? Or things like integral of sine to the 4, x dx. How would one do questions like this? That's sort of what we're going to be doing in these questions today. So let's first deal with, let me delete the first. Integrals of the form cos to the power of mx dx. Okay, of course we know if m equals 1, we're just going to have the integral of cos x dx. Very nice. Okay, well, what if you have, let's say, m equals 2? Actually, we can just quickly evaluate this as sine x plus 2. Okay, if m equals 2, then you have the cos to the power of 2x dx. To utilize such a question, or to utilize this, what we have to do is we have to say, oh, I have that one rule. It's on my reference sheet, and it says if you have cos squared nx, then this equals a half of 1 plus cos 2nx. Sick. Okay, that comes from the double angle forms and is just rearranged. So this ends up being the integral, or half of the integral, of 1 plus cos of 2x dx. Wonderful. Okay, and then we get 1, and then this is just x plus a half of sine 2x plus c, which is just x on 2 plus a quarter of sine 2x. Okay, so that's what you do if m equals 2. Now you should be already quite aware of this because we're going to get into much trickier scenarios. Okay, for example, if m equals 3, so the integral is of cos cubed x dx. We don't have a rule for cos cubed x dx, right? Like we have for the cos squareds. There's no So the trick with something like this, particularly if m is an odd number, so if m is odd, the trick is isolate one of the cosines. One of the cos x's. And you'll see why I'm going to do this. If I isolate one of the cosines and I get this as the integral of cos x times cos squared x, I can use my Pythagorean identity for cos squared and rewrite this as 1 minus sine squared x, okay? Because then my integral becomes the integral of cos x times 1 minus sine squared x dx. Why would I bother doing this? Because now I can use a careful U sub to show that this is actually just reverse chain rule, okay? Because if you see, this is a function in terms of sine x's. And what's the derivative of sine x? The derivative of sine x is just cos x. So the derivative of that is present. But to show this clearly, I'm going to be using U sub. So I'm going to say, let U equal sine x. Now it's up to you whether you actually want to bother doing this new exam, but I think it makes this make sense. Okay, so then du dx equals cosine x, which means du equals cosine x dx. Okay, perfect. If du equals cosine x dx, that means this integral can be rewritten as 1 minus u squared du. Now this is just a polynomial, isn't it? So this becomes u minus a third of u cubed plus c. Perfect. Okay. And then we just go back to our original. So we say this is sine x minus a third of sine cubed x plus c. Okay. So particularly if m is odd, other than cos x being to the power of 1, that's sort of easy. But for m being an odd number, always isolate one of the cosines and rearrange whatever's left such that it is in terms of sine. Okay, because then you can let u equal to sine and then you get some easy polynomial which you can integrate, because that extra cos x that you isolated kind of becomes the derivative of those sines, which accounts for the chain rule. Okay, so that's why you're going to do that. In fact, I'll just give you an example for you to do now, where m is also odd. So what about if, I know I was skipping a few numbers, so what if m equals 5? Okay, and now you have the integral of cos to the 5x dx. Again, m is odd, so it makes sense to isolate one of the cosines and then take it from here. So pause the video and have a go. Okay, unpause the video. And now let's go through this. So as I said, isolate one of the cosines. So this is going to be the integral of cos x times cos to the 4x dx. Now this cos to the 4x is the same as saying cos squared x all squared. And I know what cos squared x is. It's 1 minus sine squared x. So that's the power of 2 like this. Okay, perfect. Now my integral becomes the integral of cos x, which is the one I isolated, times 1 minus sine squared x all squared. So actually, am I going to leave it like that? No, I'm not. Let me say 1 minus sine squared. Actually, no, we'll leave that. Okay. So if I let u equal sine x, I can see again du equals cos x dx, and rearrange and like subbing that all in, we get 1 minus u squared all squared, and then du. I look, I have to expand it, right? I can't just add on to the power, divide by new power, because if I divide by the derivative of the inside, I'm dividing by a minus 2u, and I can't introduce new u's like that. So I have to expand. But that's okay. We know how to expand. And then from here, of course, you could have expanded from here if you'd like, but I just don't want to keep expanding with sine x's, so I'm doing it with the u's instead. And then this integral becomes that. And then going back and subbing in all of our u's. So we get sine x minus 2 over 3, and then sine, oh, we can write this differently actually. Sine cubed x plus 1 over 5, sine to the 5x plus c. Perfect. I hope that makes sense to everyone. And also the reason why we have to isolate one of the cosines. Wonderful, wonderful, wonderful. Okay, what if we have, so where do we stop at? I think we did m equals 3 and then we jumped to m equals 5. So we missed m equals 4. So m equals 4. This is going to give us a good example for how you would treat kind of like the rest of the even powers of cosine. Okay, so if m equals 4, then we have the integral of cos to the 4 x dx. Okay, trick is, how are we going to integrate something like this? Well, we have to use our identity for cos squared x. So what you're going to do is rewrite this as the integral of cos squared x all squared dx. And you'll see why. What did I say cos squared equals? Well, maybe I didn't say it, but I know it is on my reference sheet. Because if we use our identity at the bottom of, I think, like page 2, we have cos squared x equals a half of 1 plus cos 2x. Perfect. So now, as we move to this question, we can say, well, that cos squared x is actually just really 1 plus cos 2x all over 2 and squared, like this. I'm going to expand it now, and you're going to see what's going to happen. We have, obviously, the denominator being squared is going to be 4, so I'm just going to take the quarter out. And then expanding this one using like our perfect square, it's going to be 1 plus 2 cos 2x, and then plus cos squared 2x dx. I think you can see this is quite easy to integrate. This is quite easy to integrate, but here we have another cos squared. Okay, so how are you going to do this? Well, you then have to go and say that little identity I have at the bottom of my reference sheet, I have to apply that again, because generally the reference sheet has it written like this, I believe. Cos squared nx equals a half of 1 plus cos of 2nx. Okay, that's so close to the edge. Let me fix this up like that. So that means now that you have cos squared 2x, this thing here is going to equal a half of 1 plus cos of double that argument. So this is the argument's 2x, it's always going to be double that, which is why you have, like, if this is nx, it's just 2 of nx. So this is going to be cos of 4x, like that. Wonderful. So now my integral becomes a quarter of the integral of 1 plus 2 cos 2x plus, and then that expanded is a half plus a half of cos of 4x dx. Okay. And then again, this is just a quarter, and then let me just clean this up. That's 3 over 2, so that 1 plus that half, and then plus 2 cos 2x plus a half of cos of 4x. And now you can just integrate. So quarter, 3 over 2 x plus, and then this is 2 cos 2x, but then the cosine goes to sine, and then I've got to divide by the derivative of the inside, and this one also goes to sine, but I've got to divide by the derivative of the inside, like that. And then this becomes 3 over 8x plus a quarter of sine 2x, and then plus 1 on 8 sine 4x plus 2. You can take out an 8th if you'd like. Then it becomes 3x plus 2 sine. Yeah, plus 2 sine. If I take out an 8. No, a 4, my bad. And then plus a cos of, no, a 2, sorry, and then plus a sine of 4x. Anyway, you get the idea. So that's how you would do that one. Perfect. Of course, if m equals 6, you would do the exact same thing, right? We're not going to do that because that's going to take ages. And I highly doubt you're going to get a question that says cos to the power of 6. But you can see, it kind of makes sense what you would do, right? If m equals 6, you have the integral of cos to the 6x dx. You would have to write this as integral of cos squared x to the power of 3. Then you would have to expand this cubic, because this would be 1 minus sine squared x. Actually, no, my bad, you don't need to do that. What am I doing? That's the half of 1 plus cos 2x, isn't it? And then you would expand that. Then you'd get a square term, and yeah, it's just a mess. But you can see that that's kind of like, that's the pattern for a question like this. Okay, perfect. Just tie this up so it gets out of the way. Wonderful. Okay, a little bit of a mess that is. Anyway, that is for cosine. You can also do the same for sine. In fact, the rules are very similar. If sine of x has an odd power, you would isolate one of the signs. You'd replace everything else with cosines, as opposed to what we did here, which is isolate a cosine and replace everything else with sines. Okay, if it's an odd one, you would do the exact same thing. So what I'm going to do is just give you a few examples to do for powers of sine x. Okay, so I think I wrote this down as the integral of cos to the mx. What if we had here the integral of sine to the power of m x dx? Let's make that. Okay, actually, I don't want that. Okay, just to evaluate a few of these. I'm only going to go up to, I'm not sure, the integral of sine x dx, the integral of sine squared. Just to make it a bit spicy, I'm going to put a 2x there. The integral of sine cubed x dx, and let's say 0 to pi over 3. And then let's have the integral of sine to the power of 4 x dx. And which one else should I do? Okay, and let's do the integral of sine to the power of 7 x dx. Have a go, people. Oh, this is very laggy, isn't it? Okay, that should be good now. Okay, good. Have a go and unpause when you are ready to go through the answers. Actually have a genuine attempt at them all, or else you'd be very annoyed. Now, once you've unpaused, let's go through. I should probably mark them in as like A, B, C, D, E. So for A, we have the integral of sine of x dx. This is super obvious. It's just minus cos x plus c. I sure I said it's super obvious and I fumble. Did I fumble? No. I'm good. Okay, B, sine squared of 2x. So this is where you have to use the rule on your reference sheet. And of course, this becomes the integral of, I'll put the half at the front, 1 minus cos of double that angle, so 4x dx. And then this becomes a half of x and then minus a quarter of sine of 4x plus c. So x on 2 minus an 8th of sine of 4x plus c. Beautiful. Okay. Yep. C, what was C? So for same thing with what we did with cosine to the power of 3. So one of those odd powers was we had to go and isolate one of the cosines. Here, I'm going to isolate one of the sines. So this is going to be the integral from 0 to, I'll write this in blue actually. the integral from 0 to pound 3, 1 of the sine x's times the sine squared x dx. And then I'm going to go and rearrange that sine squared as 1 minus cos squared. Perfect. Okay, let u equal to the inside. That is the cos x. Okay, because you have the derivative of the cosine, it's just minus sine, so that sine cancel off. So letting u equal cos x means du on dx equals minus sine x, which means du equals minus sine x dx, which means I just need to put a minus there and a minus there. Now, because I have bounds, I have to write them as u bounds or u limits, so that's going to be x there and u there. 0 to pi and 3. When cosine of 0 is 1, and then cosine of pi and 3 is a half. So this becomes the integral minus the integral from 1 to a half. All of this goes to du, and that becomes 1 minus u squared du, like this. You know, you can use this negative to swap this and make it the integral from a half to 1 minus u squared du. And then finding this integral is u minus a third of u cubed, like that. Subbing in, we get 1 minus a third. That's written atrociously. 1 minus a third minus, and then a half minus a third of a half cubed. Bruh. 2 over 3 minus a half plus a third times an eighth, 1 on 24. And then adding these all together, so 16 minus 12 is 4. 4 plus 1 is 5, so 5 on 24. There you go. There you go. That's that. Not bad. And then D, we're almost there. What did we do for even powers of cosine? Well, we wrote it as the integral of sine squared x all squared dx. And then sine squared from our double angle for cosine is given as, I think the rule is if you have sine squared nx, it's a half of 1 minus cos of 2nx. Again, I'm awfully too close to that corner. So this becomes the integral. I don't know why that closed off. Oh, that's not good. Okay, I think something went wrong, but hopefully nothing cut out too bad. So from this, we're just going to say the integral of, and then rearrange that, or replace that sine squared x with, it should be 1 minus cos of 2 and of 2x rather. Over 2 all squared dx. Now, taking out that quarter, because that 2 in the denominator squared is 4, we're going to get 1 and 4, and then we're going to expand the numerator and get 1 minus 2 cos 2x plus cos squared 2x dx. Lovely. And again, that cos squared 2x can now be replaced. Unfortunately, seriously not bothered, but I think this is, so expanding that is just that. Okay, so now when we have this integral, it's going to be 1 minus 2 cos 2x plus a half, and then plus a half of cos 4x dx. there's a half and a 1, so that comes together to give you 3/2. And then this together, you can integrate it. Actually, no. 3 on 2x, and that becomes minus 2/2, so minus sine of 2x, and then plus 1 on 8 sine of 4x plus c. And then of course you can expand and you can get whatever you get from there. But that's that thing. I hope that helps. Okay, and I think we have one more, which I've begrudgingly must do. This is E. So to integrate any high power which is odd, what you must do is isolate one of them and then write it as sine x times sine x to the power of an even number, and then recognize that there is just sine squared x, but put to the power of 3, because you have a rearrangement for sine squared as 1 minus cos squared x to the power of 3, like that. And then all you got to do is let u equal cos x. So let u equal to the 1 that's got that the higher power, because that would just be the derivative or partial part of the derivative. So letting u equal cosine x, we get du on dx equaling minus sine x, which means du equals minus sine x dx. I need a negative, I'll chuck a negative there and there. This gives us minus the integral. That minus sine x dx goes away, and then you end up with 1 minus u squared to the power of 3 du. Again, expanding this, we get 1 minus, and it is 3 times the first term squared times the second term, plus 3 times the first term squared times the first term times the second term squared, like that. I don't know if I'm making sense, but you have your binomial expansion of this, and then minus, and then that's u to the power of 6 du. Okay, minus, and then the integral of 1 plus, no, this should be like that. Minus u to the 6 du, and this is u minus 3/3 u cubed, and then plus 3/5 u to the 5 minus 1/7 u to the 7 plus c, and then this becomes minus u plus u cubed minus 3/5 u to the 5 plus 1/7 u to the 7 plus c, and then we just go back and we say, but oh, I let u equal cos x, so this becomes minus cos x plus cos cubed x minus 3/5 plus to the 5x plus 1/7 plus to the 7x plus c. Perfect. Perfect. So those are those. How about if you have powers of cosine and sine, but put together? Okay, so you had the integral, this is a new thing, of cos to the power of m times sine to the power of n dx. Okay. Now, what happens if we have different cases? The first case, so case 1, not that I want you to remember them as cases, but this is just a good way to write them out. Case 1, m and n are both even. Okay, so let's see how this would work. What if I had the integral of 4 cos squared x sine squared x from 0 to pi over 2 dx? particularly when the powers are the same, we can use, actually when the powers are the same, not particularly, when the powers are the same, we can rewrite this as, oh, you know, I'm going to take that 4 out. I know, you'll see. I'm going to write this as cos x sine x or squared dx. Don't we have a double angle identity for sine 2x? Yes, we do. A double angle identity tells us if you have sine of 2x, it equals 2 sine x cos x. Okay? So that means if you have sine x, if you have cos x sine x here, that's simply just a half of this, which means it's a half of that. So it becomes 4 times the integral from 0 to pi on 2 of, and then it's 1 over 2 sine of 2x or squared dx like that. Okay, now you could have then just gone and squared this if you wanted, and you would have gotten exactly that one, but I'm just showing you that like generally you're not going to have that 4. So it's okay to do it like this, and then whatever that square goes to this, you can just take it out. Anyway, when you square that, half it becomes a quarter, and then the 4 and that quarter cancel, and you end up with just 0 pi on 2 of sine squared 2x dx. And then you're in that annoying scenario we had before, where there's that double angle for cosine, and you can just rearrange this as a half of the integral from 0 to pi on 2 of 1 minus cos of 4x dx. And then this becomes a half of, and then we have x minus 1 on 4 sine 4x from 0 to pi on 2. And subbing in what we have a half of then pi on 2 minus a quarter of sine of, that's 2 pi, then minus, and then it's 0 minus a quarter of sine of, that's just 0. Anyway, that's 0, that's 0, that's 0. So you end up with just a half of pi on 2, which is pi on 4. Sick. Okay, perfect. What if you have the case where one of them is odd and the other one is even? So case 2, one is odd, the other is even. Okay, something like the integral of cos and then cubed x sine squared x dx. What you want to do always is whichever has an odd power, isolate one of them. So in this case, the cos is put to the power of 3. So you want to isolate one of those cosines. And you'll see why that works, because as soon as I isolate one of the cosines, I get cos squared sine squared x. And then this thing here can be rearranged as 1 minus sine squared x. That takes us into one of the formulas we had before, isn't it? Because now you have 1 minus sine squared x and you have sine squared x. So when you expand this, it becomes the integral of cos x times sine squared x minus sine to the 4x. All you got to do is let u equal sine x, like what we were doing before. Because when you take du dx, you have the du, or you have the derivative already there, that cosine. Then you end up with just a polynomial integral. So du on dx equals cosine x. That means du equals cos x dx. So our integral now just becomes quite easily u squared minus u to the 4 du. Okay, and then that just becomes a third of u cubed minus fifth of u to the 5 plus c, and then subbing in back our signs. Like that, and then you're done. Okay, so do you see the premise of that? Perfect. Okay. I'll get you to do a few questions. Now, they might be of the form from before, it might be of a bit of a different form, but we shall see. So let's say I had the integral of sine to the 5x times cos to the 4x dx. Okay, have a go at this. Then also have a go at, what if I have it as, maybe the second one's quite difficult, but I want you to have a go. They're both even powers, but you might treat them a bit differently. Anyway, pause, have a go, and now unpause, because I'm going to go through them. Well, this first one is an example of one is being odd and the other one's even. So I'm going to isolate, in this case, one of the sines, not one of the cosines. And it's going to be the integral of sine x times sine to the 4x cos to the 4x dx. I'm now going to replace this sine to the 4x with 1 minus cos squared, whoopsie, or squared, because that's just sine squared, and it's sine squared to the power of 2. So sine to the 4. Perfect. Now I'm already going to let u equal to the cos x, because I want to save myself from writing out all those cosines. Then du on dx equals minus sine x, which means du equals minus sine x dx. That means I just need a negative there and a negative there. And this becomes the integral, or negative of the integral, of 1 minus u squared to the power of 2 times u to the power of 4 du. Expanding this, I'm sorry, I didn't make this super easy. Actually, no, it's still pretty easy. 1 minus 2u squared plus u to the 4, all multiplied by u to the 4 du. And then this is u to the 4 minus 2u to the 6 plus u to the 8 du. Okay. This is a problem with online lessons. I feel like there's no interaction, so I'm just speaking for like 2 hours straight. It's atrocious. Okay. And then this is minus a fifth of u to the 5, and then plus 2 over 7 u to the 7. This is minus 1 over 9 u to the 9. I already expanded the negative out. And then just going back to the other thingy that we had. What was it? Let u equal cos x. So cos to the 5x plus 2 on 7 cos to the 7x minus 1 on 9 cos to the 9x plus 6. Okay, what about the next one? Well, for the next one, we're going to get, what are your thoughts? It's actually quite a difficult integral. Did I even plan on how to do this one? No, I didn't. It might require integration by parts, to be honest. Yeah, okay. Oh, this is sick. I didn't realize I gave this question. I'm gonna write it as sine x times sine x cos to the 4x. Yeah, like that. So let's see. Let me take this to the next page. Okay. Now, what if we I'm purposely splitting it up because that just looks like chain rules. I'm gonna make this v dash. I'm gonna make that u. Okay. So now we have, if u equals sine x, we have u dash equals cos x. And if we have v dash equals sine x cos to the 4x, doesn't this just look like, if we're trying to integrate this, it looks like reverse chain, doesn't it? I have some function put to a separate power of 4, and I have this sine x, which is the derivative of that function, almost. I just need sort of like a negative there. So let's say I put a negative and then put another negative like that. This integral just becomes minus, and then add 1 to the power, divided by the new power. So my answer to this becomes uv. So minus sine x cos to the 5x on 5, and then minus, and then the integral of vu dash. So you have a minus from there. So let me just put that back there to make it a plus, and then it's going to be cos to the power of 6x on 5 dx. Let me put that 1 over 5 out the front. Okay, now I'm really not bothered to do cos to the 6, but you know how to do the integrals of cos to the 6, because we know that just like how we split it, what do we do for odd or even powers? Even here, we gave an example of the cosine. Did we do cos to the 6? No, we just did cos to the 4. We wrote it as we use this to replace the cos squared. So you just do that, then it'll be to the power of 3. I think we discussed it at least. Oh yeah, we didn't do it, but you write to the power of 3, then you'd expand it, then you'd work from there. But obviously we weren't going to do that because it takes ages. Maybe this is just a poor choice of question on my part, but I'm really not in the mood for doing that one. Lovely, lovely, lovely. Okay, so once you've had a go at those, I think we're basically set. How about if we have integrals with secs and tans? So okay, first of all, we have to know the integrals of tan x, and we have to know the integral of sec x. Now we have previously discussed that the integral of tan x simply is just minus ln of the absolute of cos x plus c, and then we have discussed that this is just ln of sec x plus tan x and plus c, like that. Okay, perfect. We know those ones. So what if we had an integral that was, let's say, the integral of tan squared x? How do you think we would do this? Okay, I want you to at least have a go on your own, and then once you've maybe had an attempt, come back to me. Well, you have to know your Pythagorean identity. Your Pythagorean identity is 1 plus tan squared equals sec squared, which means tan squared x equals sec squared x minus 1. So this becomes the integral of sec squared x minus 1 dx. Well, we know the derivative of tan is sec squared, so that means the integral of sec squared is just tan. And then minus 1 goes to minus x, and then plus c. So we have that one. Okay. What if you had, say, the integral of tan to the power of 4x dx?
Okay, a bit of a change in scenery. So let's do this one. I'm first gonna rewrite this as tan squared x times tan squared x. I think you'll see why as I go along. Isolating a tan squared x allows me to replace one of them with sec squared x minus 1. By doing this, I then get the integral of tan squared x times sec squared x minus tan squared x dx, like this. Now I'm going to split it up, and I'm going to make it so that it's the integral of tan squared x times sec squared x dx minus the integral of tan squared x dx. Okay, perfect. The reason why this is necessary is because now for this one here, well, isn't this, if I rewrite it maybe as like 10x to the power of 2, isn't it sort of the form f of x put to a separate power, like the n, and then isn't that kind of like the f dash x? So it's kind of reverse chain rule, isn't it? So sort of, because you have the exact derivative of the 10x present, you can say it's just 10x add on to the power, so to the power of 3, and then divided by 3. But if you can't see that so clearly, you can just do u sub. So by letting u equal to, here, let u equal to 10x, and then here, this is 4, we'll call it this one here is the I. Okay, that or that 1, so for that first integral, not for the second one. Let u equal 10x, du on dx equals sec squared x, and then that means du equals sec squared x dx. Perfect. So now this integral becomes the integral of u squared du minus, and then we just do this one. Now for this, I'm going to replace this again with sec squared x minus 1. Like that. Perfect. Integrating u squared with respect to u is just going to be a third of u cubed. Then minus, and then the integral of sec squared, well, isn't that just 10? So put a bracket, 10x, and the integral of minus 1 is minus x, and then plus c. And then we just go and say, well, u equal 10x. So that's this. Perfect. So that's your final answer. Now you might say, if I had to replace this tan squared x with sec squared minus 1, and then I want to replace this tan squared x with sec squared minus 1, you know, isn't that sort of the same as replacing everything here with, like, both of them with sec squared minus 1? No, it isn't. Because if you did that, then your entire, when you expand it, will just be in terms of sec squareds. Okay, and that's not going to help you. You actually still need a tan squared for this. Okay, remember, the derivative of 10x is sec squared. So it's very easy afterwards to just do reverse chain rule because you have that derivative of the 10 always present. Wonderful. Okay. What else can we do? What if we had something like, I'm kind of just showing you different questions. The integral from 0 to pi on 4 of sec to the power of 4x tan squared x dx. Okay. Well, what I'm going to do again is isolate. Watch, this is quite smart. I'm going to isolate a sec squared x. This works, by the way, this works when you have an odd power, when you have an even power of sec. You'll notice why. If I isolate one of the sec squared x's, I'll be left with a sec squared x like this. Now, what is sec squared x? Isn't that just 1 plus tan squared? Indeed it is. So you end up with the integral from 0 to pi on 4 of sec squared x, and then if this is 1 plus tan squared x times tan squared x, I'm just going to expand that and make it tan squared x plus tan to the 4x dx. Why is this a good form? Because now this here, if you let u equal to tan x, you have the derivative of that tan x already present because it's sec squared. So isolating the sec squared is perfect, but it only works if sec is put to an even power, because if I had to isolate a sec squared, I need to ensure I have an even power of sec left over so that I can replace it with 1 plus tan squared. Okay, even if this was sec to the 4, I would have made it sec squared all squared. Then it would have been 1 plus tan squared all squared, like that. Perfect. Now, to make life easy, we're going to let u equal to tan x. That means du equals sec squared x dx. And we have to replace our limits or our bounds as well. So 0 and pi on 4. 10 of 0 is 0, 10 of pi on 4 is 1. So this just becomes the integral from 0 to 1 of this thing goes to du, and we end up with u squared plus u to the 4 du. Adding 1 to the power divided by the new power. And then subbing in, we get 1 over 3 plus 1 over 5 minus 0 plus 0. And this should give you 8 over 15. Perfect. Wonderful, wonderful. Okay. What if you didn't have it of that form? What if you had it of this form instead? Let's say it was the integral from 0 to pi on 3 of sec cubed x tan x dx. Doesn't seem like I'm going to be what's the word? Isolating a sec squared. Because if I do, then I'm going to be left with sec x tan x. What I'm going to do instead is isolate a sec x tan x. Well, I mean, that's actually kind of the same, but it's not for the purpose of isolating the sec squared. It's for the purpose of isolating the sec x tan x. You'll see what I mean. So we have this. I'm going to put the sec x tan x here, and I'll put the sec squared x here. What's the derivative of sec x? Isn't it sec x tan x? The answer is yes, it is. So it seems like I have some function, sec x, put to a separate power of 2, and then I have the derivative of that function present. So it's reverse chain rule. But to show this a lot clearer, I'm going to let u equal to sec x in this scenario. The du is going to equal sec x tan x dx. And then replacing the bounds, we have x and u bounds. 0, pi on 3. Sec of 0, well, that's 1. And then sec of pi on 3 is 2. And now this thing becomes the du, and this becomes u squared. Okay, so adding 1 to the power divided by the new power, we get a third of u cubed from 1 to 2. And then 2 cubed is 8, so it's 8 on 3 minus 1 on 3, which is 7 on 3. Perfect. What if we had the integral? I don't actually know how this is going to go. We won't do any bounds. Sec cubed x tan squared x. Anyone have any thoughts? I feel like maybe we need to do, actually no. Let's make this tan cubed x. Tell me what you think we should do for this. Actually, tell me, try out some ways to do this. Okay, maybe you want to isolate a sec squared. Maybe you want to isolate a sec x tan x. Because either way, it's either going to be reverse chain rule for sec or reverse chain rule for tan. So it's up to you. I think we should isolate a sec x tan x. And then we're left with sec squared x, tan squared x. Okay, how does this help? Well, what does tan squared x equal? Doesn't it equal sec squared x minus 1? Perfect. So my integral becomes this thing here, And then it becomes sec to the power of 4x minus sec squared x dx. Now let u equal to the sec to the 4. Oh, sorry, just the sec. Just a sec. Du equals sec x tan x dx. And you can tell I'm kind of getting bored of these questions because they're all very similar. It's just test out a few methods, and the more you practice, the easier they become. It becomes u to the 4 minus u squared du. And then this becomes a fifth of u to the 5 minus a third of u cubed. Then what am I doing? Plus c. And then just going back to our original, we're going to have sec to the 5x minus a third of sec to the 3x plus c. Wonderful. Okay, I want you to have a go at this integral here, sec cubed x dx. Attempt any which way you wish. If I replace this with anything, I don't know if I get anywhere. Like, if I replace the sec squared with 10 squared x plus 1, I don't know if I'm going to get somewhere because I just got to where I was before. I don't want to do integration by parts. Should I do integration by parts? Okay, let's do integration by parts. See if this works. I'm going to make this equal to my v dash and make this equal to my u. Because if it's the other way around, if this was my v dash, I have to integrate it and I'm going to get lins in it. And then I have to take the integral of v u dash, and taking the integral with already a ln of sec x plus 10x is a mess. So let's say u equals sec x, u dash equals sec x 10x. V dash equals sec squared x, which means v equals 10x. So bringing this together, we get vu, so sec x 10x, minus, and then the integral of vu dash sec x 10 squared x dx. Isn't it? No. Okay. Do we just expand this out and see what happens? So this becomes sec x 10. Wait. Watch. We just put a bracket around this, and it's going to be the integral of sec cubed x minus dx, we should put it, then minus the integral of sec x dx. Isn't it? I just expanded this sec x to each of those and then split them up as separate integrals. Now, if I expand this, if this here was like an integral, that's the same integral. So if I just like add that to both sides, I get 2 of the integral that I want equals sec x 10x, and then plus the integral of sec x, which is just ln of sec x plus 10x. And then dividing both by 2. Bro. That was abysmal on my part. There we go. Jeez. Okay. Okay. Good. Alrighty. Look, there's this other type of question you could get. It's kind of boring, but it is when you have, we call it products to sums. I'm not even really going to go over more than one example of this. Products to sums is when you have, say, the integral of cos 3x cos 2x, obviously, there's no like exact way to do this. There's no way to combine them, but there is a way to split it up, because I think on our reference sheet, we have the expansions of them. Let me find the reference sheet and chuck this in, and you'll see what I'm talking about. The very bottom of like page 2, I believe. This rubbish. Okay, lovely. It's not even. Whatever. Anyway, there are a few of them. They're on your reference sheet. You can just look them up. But if you have, I think it's like cos, how was it written? I'll just open it up from here. If you have cos A, cos B, cos B, this equals a half of, and then it's cos of A minus B, and then plus cos of A plus B. Okay, so this integral here becomes equal to a half of the integral of cos of A minus B, so cos of 3x minus 2x, which is cos of x, and then plus cos of 5x dx. Sick. We know what this is. That's just sine x. That's just a fifth of sine 5x plus c. Okay, so if you get a question like that, it's really not that difficult. And the last thing that you can get is something that's of the form of this. You might need t substitution. So remember t sub, so your t formula I used to convert, remember when we did this back in year 11, they used to convert trig equations into algebraic equations, which are a lot easier to solve. And then you can just, I guess, solve it as per usual and then go back and find the angles. Well, here, it's kind of a similar process. This trig integral is quite difficult, but we can potentially write it as the integral of some algebraic expression, and we know many, many ways to solve the integrals of algebraic expressions. Okay, so you're going to start off always with how we define our t forms, which is let t equal tan of x on 2. Of course, you're using x on 2 because the angles used here are x. If the angles here were 2x, you would say let t equal tan of x. So just, it should always be a half of whatever angle is in your expression. Perfect. This is a form of u sub, except it's with our t form. So you still need to replace our bounds and you need to replace this dx. We also know that cos x, it's given on our reference sheet, is given by 1 minus t squared on 1 plus t squared. So that helps in replacing this. Let's also replace our bounds actually, now that we're here. X and t. Okay. So 0 and pi over 2. When tan of 0 is 0, tan of pi 2 over 2 is tan of pi on 4, which is 1. So that's life. That makes life super easy. Now, what you're not going to do, this is definitely not what you're going to do. You're not going to take this t equals tan of x over 2 and differentiate both sides. So this is a don't. Take dt dx. Because then you're going to get sec squared x on 2. And I feel like that's more annoying. I do it differently. I do it like a mad dog. I say, let's write this in purple, the color of mad dogs. And I say, write it as x over 2 equals tan inverse of t. Okay? And then multiply both sides by that 2. And then take dx dt equals 2. And then what's the derivative of inverse tan of t? It's just 1 over 1 plus t squared. Bro, this is so easy. Now you have a perfect substitution for the dx in your integral. Instead of going, oh yeah, now I have sec squared, but I know 10 of x over 2 is t. Let me set up a triangle with angle x over 2. Well, that's t over 2, and then you find the hypotenuse and you take sec and then you square it. I feel like this takes ages. Instead, be a mad dog like me and do this. Okay? So now you come to this one here, and you say, okay, this becomes the integral from 0 to 1 of that 4 stays there, I guess, 3 plus 5, and then bracket 1 minus t squared over 1 plus t squared times 2 over, make sure your lines line up. This is quite important, those fraction lines. 1 plus t squared dt. Good. This 1 plus t squared is going to get multiplied by this denominator, which means this is going to get multiplied by the 3, and then it's also going to get multiplied by this. Perfect. I'm going to take this 4 and this 2 out because I feel like that's just unnecessary. It's going to be 8 integral from 0 to 1 of 1 over. Now, when you multiply this by this, you're just going to get 3 plus 3t squared. When you multiply this by this, that cancels off, and you just get given the 5 minus 5t squared by just expanding that out. And that's dt. Okay. So 8 integral 0 to 1, 1 over, and then what is this? 8 minus 2t squared. Okay, I'm going to factor out a 2 from the denominator. Eight over 2, integral from 0 to 1 of 1 over, and then this is when you factor out a 2, it's 4 minus t squared dt. Okay, can we integrate this? Yeah, we can. We have to use partial fractions. So you're going to say, now, that's just 4. Now, let 1 over, now 4 minus t squared is 2 plus t times 2 minus t equal something as a over 2 plus t plus b over 2 minus t. By multiplying this entire thing by 2 plus t times 2 minus t, you get 1 equals a times 2 minus t plus b times 2 plus t. If you let t equal 2, 2 minus 2 is 0, this just goes, and then you get b equal, or then you get 1 equals 4b, which means b equals a quarter. Now, if you let t equal minus 2, 2 minus 2 is 0, this goes away. And then here you get 2 minus minus 2, which is 4. So then you get 1 equals 4a, and that means a equals 1 over 4. Ah, sick. So both of them are 1 and 4, which makes our life even easier because now even this 4 gets cancelled off. Because now it becomes integral from 0 to 1 of 4. You kind of have that quarter over 2 plus t plus a quarter over 2 minus t. But if you take out this quarter, it comes over 4 and then those cancel. So you end up with this. Zero to 1 of 1 over 2 plus t plus 1 over 2 minus t dt. Of course, if you integrate this, this becomes ln of 2 plus t minus ln of 2 minus t. 0 to 1. You need a minus because the derivative of this is a minus. So then you put a minus out, like if you split up the integrals, but I'm not doing that. This becomes ln of 3 minus ln of 1 minus ln of 2 minus ln of 2. Yeah, facts. So it's just ln 3. Sick. Okay, so that's a lot of work actually, but I don't really know any other way to do this other than what we did here. So very nice, very nice. Okay, that sets you up well for Trig's integration. Bye. Let me pause. How do I end this?